Okay, so now let us talk about the neural networks. So, of course, I have the input layer and then I have the hidden layer, and there are weights around over here, and then the output goes into the output layer. So let's take this as the representative neural network. So I apply the input here and I get the output here, where this is the hidden layer. There could be one or more hidden layer. Now I need to train the neural network. So traditionally I use the algorithm which is the backpropagation algorithm. And what the algorithm does is that it takes the gradient of the output with respect to the inputs, and it says the weight vector is displaced in the same direction. And of course, what does it mean is that if this is my weight space, so I've got all the value of the weights over here with the loss function. So at starting, I'm at any random configuration, say over here. This is the direction of the gradient, and I apply the correction in the same this thing. So I move like this over here, and I stop over here where the gradient is 0. So that's the backpropagation algorithm. And therefore, it's inquisitive. If I could learn the weights of a neural network, learn the weights and biases of a neural network by the application of a genetic algorithm, because in genetic algorithm we were also doing exactly the same thing, wherein I had a fitness landscape like this. There was a loss, this was my parameter space, or let's say the weight space, and there was something over here, and I do exactly the same thing. So let's compare the backpropagation algorithm with the genetic algorithm, and to add flavor, let's add a hill climbing algorithm. So the backpropagation algorithm starts off from a random place, takes a gradient and moves in the direction of gradient. The genetic algorithm takes in a random population pool, does crossover mutation and everything, it goes over here. And the hill climbing algorithm, of course, does exactly the same thing. So it moves in a random direction. If it's better, it accepts it. If it's not better, it does not. So eventually it also moves like this. So let's compare the three algorithms and what will happen if I use it for training of the neural network. So the first is, of course, the convergence time. The backpropagation algorithm is the fastest. The hill climbing will take more time because it will try random directions. The backpropagation algorithm always knew the direction it has to go, while hill climbing has to try multiple direction. And genetic algorithm, too many individuals, so it will be slow. However, both these algorithms are local algorithm, and because they are local algorithm, so prone to get stuck at local optima. So this is high, it mostly will get stuck in a local optima, and you mostly get to the global, you mostly get into the global optima. And therefore, if you say that time is not my concern, so if you say time is not my concern, therefore you will choose in probably this algorithm. But as it so happens that there's another advantage of the genetic algorithm. A neural network training always has two types of training. The first is the architecture, number of hidden layer neurons, which neuron is connected to which other neuron, which is not connected. You cannot assume fully connected is the best network. So these days we talk about CNNs, it's limited weight connections. So weight sharing and the limited connection is what makes it different to normal neural networks. So all connected is definitely not the best architecture. So what is learned? Here, weights and biases only. Here also weights and biases only. And here you have weights, biases, and architecture. So that's another advantage, that it will learn the weight, it will learn the bias, and it will also learn the architecture. So that's also mostly why I would probably go with the genetic algorithm, because I won't have to assume it's fully connected, because backpropagation algorithm doesn't find out which neuron should be connected to which other neuron, but the genetic algorithm will be able to find that out. Backpropagation algorithm cannot optimize the number of hidden layer neurons. The genetic algorithm should be able to do it. So my motivation over here is called as Neuro-Evolution, which means using genetic algorithm to learn a neural network. And of course, I'll not be talking about any bit of neural network over here. That's a part of another course. So it's using genetic algorithm in order to learn a neural network. So there's nothing unusual about it. Let's take a neural network, a simple neural network around over here. So 2 input neurons, 3 hidden layer neurons, and output neurons, all connected. And so that's input 1, that's input 2, that's the output. So that's input 1, that's input 2, that's the output. And let me add the biases as well. So these are the biases. And this is the bias for the output neuron. So let's give in weight some value. So I said I'll use a genetic algorithm to train a neural network for a variable architecture, but as I now realize that maybe a variable architecture is a hard thing to do. So let's say that we fix the architecture to exactly this, or let's train a neural network for a fixed architecture. So I fixed the architecture, and this one is of course what is called as my phenotype. So I need to convert it into what will be called as a genotype in order to do the evolution. So the architecture is fixed. It need not be optimized. So what is optimized? W0, W1, W2, W3, all the way up to W12. And note that I can, given a genotype, I can get a phenotype. Given a phenotype, I can get a genotype. So let's say the inputs are normalized to lie between 0 and 1, in which case the weights will also lie between -1 and 1, minus negatives to model the inverse relationship where increase of something leads to a decrease in output, and so on. So given this, I can note down all the weights over here and get this, and given this, I can take a blank neural network in whatever the neural network is in the library, whichever library you are using. So it'll come with random weights, just override the weights to these. So from this you can get this, and from this you can get this. From phenotype you can get a genotype, and from genotype you can get a phenotype. So what's the first thing that I do is I make a random population. So this was just one random individual. Like this, I make in many, many, many random individuals. And so on. So that's individual 1, individual 2, and so on, individual n. And this is weight 0, weight 1, weight 2, all the way up to weight 12. So the first thing that I need to do is that I need to calculate the fitness value of any individual. So let's do it. So let's say this is individual I and the weights are, and so on. So what do I do is that I take in my whichever machine learning library am I using, I take exactly the same neural network. The architecture is fixed. So I take 2 input layer neurons, 3 hidden layer neurons, 1 output layer neurons, and I note down all these weights, 0.8, so this is replaced with a 0.8, minus 1.1, so this is replaced with a minus 1.1, 0.7, so this is replaced with a 0.7, so I keep on overwriting these weights, 0.1, 0.1, so I replace all the weights with these values. So the old library generated random weights are gone and my new weights are around over here. And this as a library is my actual neural network. So the first step in fitness evaluation is where I convert a genotype into a phenotype. Now it's a phenotype, it's an object of neural network in whichever library am I using. And therefore what I'll do is I'll calculate the fitness value. So the loss function of this individual okay, the X has already been used. So loss function of this individual so let's call it as theta 0, theta 1, theta 2, theta 3, all the way up to theta n. So the loss function of an individual I is exactly the same loss function that the backpropagation algorithm uses. So that's I is equal to 1 to number of training data. So this neural network, let's call the function as ANN, applied on the training data xi, given the weights as this theta I, minus the output, minus the target. So let's say the target is yi, which is already given, the whole square. If you want, you can do a half. Otherwise, as of now, I'm not taking a derivative, but because we use it there, let me take it here as well. Plus lambda times the regularization parameter. So it's the same loss function as used by the backpropagation algorithm, and we have regularization for exactly the same reason, and we've got the mean square error for exactly the same reason as we do it. So that'll give you some values that we can write it down over here. So we'll have the fitness value over here. So this is also the fitness function. So this is also the fitness value, which needs to be minimized. So it's to be minimized. So I'll get all the fitness function value over here, and of course then we know what to do. Calculate the rank. Once you calculate the rank, then you calculate the expectation value, the selection, the crossover, the mutation, the making of a new population pool, and just reiterate. So that's a genetic algorithm that's training a neural network. Now, luckily, you have the backpropagation algorithm that is also there, and therefore I can fuse the genetic algorithm and the backpropagation algorithm as explained previously into a memetic framework So we discussed three architectures out over there, and this exactly the same three architectures could actually be used around over here as well. The first is that for every JIT generation, you cluster these individuals, you get some cluster centers and apply backpropagation algorithm over there for a few iterations. The other one is the initial individuals, you expect them first to a backpropagation algorithm, all of them, and then apply the complete genetic algorithm. And the third, you apply the entire evolution, take the best individual and apply a few iterations of the backpropagation algorithm. So whichever you want, you can actually get this thing over here. So it can be fused as de facto in a standard memetic framework. Now, it really happens is that I wanted a variable architecture, and the problem with this is that it only learns the weight values, it doesn't learn the architecture. The problem is also with the training time. So in backpropagation algorithm, sometimes we say that batch learning is not possible. Let's make a sequential learning. That's also something that is done to make it avoid the local optima or escape the local optima. So here, if the training data is too large, it's a batch learning. So I'm iterating over the complete batch. It's not many batches, it's the complete batch. It's not sequential where you only train with one data, it's a complete batch. So if your training data, the magnitude that we talk about today is mammoth, then you'll of course have a problem, because the total fitness function evaluations are number of generations times number of individuals, which is large, and every fitness evaluation is iterating over the entire training data. So that's too large, which is when you would also for the training data use things like clustering or importance sampling, where you say some data is important and only that will go through the genetic algorithm.